Okay, welcome to today's Friday seminar. Today's speaker is Damiano Anselmi from Pisa University, and he will talk about from Fakeons to quantum gravity. Yeah, have fun, enjoy this talk.
Thank you very much for the invitation and the opportunity to speak here. I will talk about a theory, a quantum field theory, that I think is a very good candidate to describe quantum gravity. And it is based on a new notion, which I call Fakon, a fake particle, which is basically a new quantization prescription for particles. And it leads to very interesting physical predictions. So let me start from very general considerations. What are the basic principles of quantum field theory? We have some requirements that we do not doubt, like unitarity, for example. This is maybe the most general and basic requirement, which basically means that you do not have any particle that disappears out of nowhere or comes out of nowhere. Then locality. Our quantum field theories, for example, the standard model, are local, but actually that's just the classical Lagrangian, or what we call classical Lagrangian. In QCD, you call classical Lagrangian something that doesn't really have to do with classical physics. It's a Lagrangian of quarks and gluons. So you have locality somewhere. And then we have renormalizability. As you can see, all three are requirements that one is maybe basic and general. The other two might sound a little bit like some aesthetical requirements. What is their true meaning? Who knows? The important fact is that they work. And in the case of the standard model, they produce a basically unique theory. Well, that's not so unique. We will see in a moment. And we will see what you have to do, what you have to relax to define and make the principles work in quantum gravity. You have also fundamental symmetry requirements. I put them here because they are important, but maybe not as fundamental as these three. Global Lorentz invariance, of course, general covariance, local Lorentz invariance, and gauge invariance. Then another property that you frequently hear of is analyticity. The amplitudes, even the single Feynman diagrams, are analytic function. The S matrix is an analytic function. Actually, that's not true. The S matrix is not analytic everywhere. There are many places where it is not analytic. Those places are normally related to physical processes. And actually, it's not even true that the S matrix is non-analytic only where there are some physical processes, because there are funny things that have been studied at length in the 50s and in the 60s about the analyticity of the S matrix. But normally you call analyticity the property that tells you that if you compute a Feynman diagram in an open set, you know it everywhere by analytic continuation. So the regions where the analyticity can fail have vanishing measure. Yeah, branch cutoffs, things like that. This is something we will have to relax. We will have separate regions of non-vanishing measure, which are separately analytically but not analytically related to one another, and which I will call regionwise analyticity. So just to warm up, this is something we have to generalize. And then there is another principle, well, that is much more difficult to define. It's called causality. I will not enter into the precise definition of that because it's challenging. But anyway, we will see signs of violations of causality in quantum gravity at small distances, which means that what is violated is what we can call microcausality. If you want, you can find the discussion on the correspondence principle. This I call the set of assumptions that work for quantum field theory and quantum gravity. I call them the correspondence principle of quantum field theory and quantum gravity. You can find in this paper that you can check from my website or other archives. Let's see how these principles work in the case of Yang-Mills theory and how powerful they are. They are powerful, but they are not that powerful actually. Well, if you demand unitarity, locality, and strict renormalizability, which means that the gauge couplings should have vanishing dimension, not positive, but vanishing dimension, you have a unique answer that is in D equal 4, you have this action which is local, renormalizable, and unitary. You have fundamental symmetry requirements that are fulfilled. Which ones? Of course, global Lorentz invariance and gauge invariance. The other two we leave for gravity. You have analyticity and you have causality. Is this principle that powerful? Not really. If you think a moment, it's powerful, but not really powerful, because what you can fix uniquely is the form of the action, but not the gauge group. There is nothing that tells you that the gauge group should be the least of the three simplest gauge groups we can imagine, U1 cross SU2 cross SU3. Why is that? Is there a periodic table? Maybe in nature you have all the gauge groups and you cannot see them because they are too heavy. All of them are all confined. Why is there no SU37, SU19? So the correspondence principle, or whatever you may call it, fails here. You do not have a prediction of what the theory should be. In the matter sector, it is even worse. In the matter sector, you can basically add whatever you want to the standard model as long as your particles are sufficiently heavy and you have not seen them at low energies. Nobody can restrict the matter content of the standard model. There are some very mild restrictions, which are, of course, the low energy limit. You know which particles are light, have light masses. And there is another, this is the only restriction we have on the gauge group and the matter sector altogether, which is the cancellation of gauge anomalies. But that's not a very powerful restriction. So you know that if the gauge anomalies do not cancel, the model has to be thrown away. But if they do not cancel, you can add more particles and make them cancel. So that's not really a restriction. I view these as a sign that the correspondence principle, so the correspondence between our world, where we live in, and which inspires our physics and our intuition, and the infinitesimal world which we want to explore, well, that correspondence might be fading away. And presumably when we go to quantum gravity, even smaller and smaller distances, we will have no correspondence at all. So the question is, what about quantum gravity? Now, in quantum gravity, we will see that we will have to relax a couple of requirements, but actually in the end the result will be even, the resulting principle will be even more powerful, because the theory essentially is unique. So let me explain to you the basic ideas of this approach, and you can find also a review in one of the papers that I recently put on the archive. Consider a propagator, 1 divided by p squared minus m squared. You need to give a prescription to define amplitudes, because otherwise the poles are located exactly on the real axis. And when you integrate, you do not know how to calculate the integral in Feynman diagrams. The Feynman prescription is to put a plus I epsilon there, which displaces the poles a little bit from the real axis. And then you know how to integrate. You know which residues to compute. Fine. Now, you cannot change the sign in front of the propagator, the residue of the pole, because that would give a ghost. Why is that? We will see in a moment when we will review the unitarity equation, the optical theorem. That is a problem because this minus sign would be very useful in quantum gravity to cancel the divergences. Einstein gravity is not renormalizable, it has infinitely many divergences, and it is known how to renormalize those divergences by means of ghosts, adding a particle with a minus sign in front, which comes naturally from higher derivative theories. But a ghost destroys unitarity. So the problem of quantum gravity is that you either have a non-renormalizable theory, Einstein gravity, with infinitely many terms that are turned on by renormalization. So either you have a theory that is non-renormalizable but unitary, or you have a theory, which we will see more closely, that is renormalizable but not unitary because it has ghosts. That was the situation before this investigation. In the bubble diagram, the result of the bubble diagram is a function of the external momentum, and as a function of the external complexified energy P0, it has this analytic structure, just two branch cuts. And those are a little bit displaced from the real axis as long as you keep epsilon different from 0. Otherwise, they are on the real axis. Let's see these things more closely and what the meaning of the branch cuts are. So let's review unitarity. Unitarity is the statement that the S matrix is unitary. It satisfies S dagger S equal 1. Normally, you write S as 1 plus IT to separate the trivial part from the rest, and then the equation becomes what is written here. 2 times the imaginary part of T is equal to T dagger T, which is also known as optical theorem, generalized version of. This identity can actually be seen applied diagram by diagram. It's more powerful than what is written here, which involves the total, the complete, or non-perturbative, or whatever S matrix or T matrix. It holds diagram by diagram. And it simply says that twice the imaginary part of an amplitude, or a single, the contribution of a diagram to an amplitude, which is minus I times the diagram, is equal to T dagger T. You see, T dagger T is something, is some square, something positive. Something positive means that you don't have the freedom to play with signs if you want unitarity. And so basically the graphical version of the theorem is that twice the imaginary part of a diagram is equal to a cut diagram, and then the 2 pieces that you obtain after cutting are one, the imaginary, one the complex conjugate of the other, so they give a square, and then there is an integral of the final phase space of the final states. So that is why the sign of the propagator, this propagator here in the middle, cannot change. Because if I change that sign, I have negative, something negative here. So it cannot be a probability, or it can be a negative probability, or there are several ways to reinterpret the ghost problem, but there is always a very, very serious problem in that case. Let me review also the optical theorem in the other case we need for the talk, namely the bubble diagram. Twice the imaginary part of the minus I times the bubble diagram is equal to the diagram that you obtain by cutting the uncut diagram. And that is again a square. You see that you have the square of these 2 vertices. It's similar, but now it's reversed. This you see, this you view as incoming particle, and the 2 outgoing particles there are the virtual particles in the loop. So this tells you about something, some physical process here. That is precisely what happens above these thresholds, and that's the reason for that non-analyticity, which is the only source of this imaginary part. Because if the function were analytic, it would be completely real on the real axis. Instead, since there is a violation of analyticity, there is an imaginary part for the amplitude on the real axis, and that is what the theorem captures. Okay? So imaginary part means physical process happening, something happening there. Here the imaginary part of the propagator is only due to this, the prescription. Now, let's see what we can do, and this is the new prescription that I introduced to quantize the poles in a different way. And how I came to this idea, I will explain later in a moment. Consider the propagator 1 divided by p squared minus m squared and write it like that. P squared minus m squared divided by p squared minus m squared squared. And then you add a width like this. You keep it real. Doing this, you keep it real. You don't have an imaginary part. And then you take epsilon going to 0. However, have to be very careful because this is a delicate point. You have to take epsilon going to 0 in a totally new way, which is the reason why this was not considered. If you take this literally, it would appear to be like the principal value of that. That's not, and that's actually that's not what you have to do. And that's actually something that would lead to very bad things in quantum field theory. And the reason why it was not considered is precisely that one. Basically, go back to the... So what we are doing here with this trick is basically we are doubling the poles. You create a numerator. The numerator will never clash with analyticity, so that's fine. Ignore it. But you have a denominator which now has 4 poles. But these 4 poles, you view it from the construction, are the 2 poles that you have here, that are the 2 poles on the real axis, that have been split into pairs. And those 2 poles in the integration we normally perform are one, the left one above, and the right one below. And so let's split those poles, but the thing you naturally come up with when you do that is that the entire pair, left pair, will be still above the integration path, and the right pair will be below, which gives you this funny integration path, which is equivalent to integrating on the Euclidean axis. So that's precisely what the Wick rotation gives. If you integrate on Minkowski, you would do this, going in between. So there are 2 choices here we can make. You can integrate like this, which gives the principal value, that's very dangerous, or you can integrate coming from the Euclidean, which gives this funny integration path, which was first suggested by Lee and Wick in their Lee-Wick models 50 years ago. So that's where everything comes from studying those models. So if you come from the Euclidean, that's a repetition, you are naturally going to integrate like that. If you come from Minkowski, you're going to integrate like that. Now we show why this is wrong, why this is bad, and then we will study the only choice that we remain with. This I noticed, this was actually the first paper of this list that I published with a colleague in Rome, Uguaglietti, physicist from La Sapienza, where we showed that if you treat these, any, in general, higher derivative theories, any higher derivative theories in Minkowski, you have to throw it away because you violate the locality of counterterms. Namely, even if the theory is local, the counterterms are non-local. Something that normally never happens. It's a very simple computation, so as a warm-up for the other ones, let's pause on this. Consider this higher derivative propagator, where you have 4 poles located like this. Okay. Then you have 2 choices, integrate on Minkowski or integrate on Euclidean. They are totally different, not equivalent, because there are those 2 residues. So let's concentrate on those residues. Let's evaluate the contributions of the residues. We will see that they are non-local and divergent. And so either Minkowski and Euclidean are both wrong, or one of them is wrong. Euclidean will be right because there cannot be no local divergences there. But they will be in Minkowski. The bubble diagram, after you integrate, this is the bubble diagram. Product of two propagators, integral on the loop space momentum k, and integral on the loop energy k0. So let's assume that we integrate in Minkowski, and we pick this residue. What is the ultraviolet behavior of these two propagators? Normally, you say this is a higher derivative theory. It is well behaved in the ultraviolet. 1 divided by k squared squared. No problem with renormalization. That's false in Minkowski. That's true in the Euclidean, but that's false in Minkowski because there is k squared equals 0. There is a light form. And so when you compute this residue, you will see that the ultraviolet behavior of the propagator of which you compute the residue is, as usual, 1 over frequency, 1 over k. But the other one has k squared on shell of the first one. And k squared is a constant, so it cannot make the integral fall off rapidly in the ultraviolet. Since this is a constant, the prevailing term, the dominant term, is the second one, p dot k, which means that you have a depressed power counting that makes the theory diverge even if it was supposed to be convergent, and an inference singularity, which gives rise to non-local divergences like 1 over p squared. So the theory has to be thrown away because one of the two, and you will imagine that it is the Minkowski one, because in the Euclidean that residue will be compensated by this other residue. In Minkowski, that residue will be doubled by this. You can check that it will work like that. So when I published this paper that showed that Minkowski higher derivative theories are inconsistent, I gave my PhD student Marco Piva a project. Let's now show that the Lee-Wick models are inconsistent. I don't know, I like to show that things are inconsistent. So I could not believe that higher derivative theories are consistent or could be made consistent. So we went back to these theories. And why? It's also because the Wick rotation is the only option we remained with, the Wick rotation of the Euclidean version of the theory, because of the reasons just explained. And we will see many things that happen caused by the presence of those poles in between your rotation, among which one of them is that the Wick rotation is not analytic. And it leads to a relation with the Lee-Wick models. Lee-Wick in '69 published a couple of papers. What was their purpose? Some people ask me, what was their purpose for trying to quantize higher derivative theories? They wanted a finite theory of quantum electrodynamics. And indeed, you can achieve that. The point is that the formulation of their ideas was not complete, and so the models have not been accepted. Maybe they have been surrounded with skepticism, and myself, I was trying to disprove them. Why? Soon it was noticed that they violate Lorentz invariance. We'll see why in a moment. They violate analyticity, but that's the minimum of the problem. See, Katkowski and a non-analytic S matrix. That's not a violation of anything. Analyticity is not a physical principle, so, but that's a fact. It violates analyticity. Well, Katkowski and others tried to complete the work of Lee and Wick, and they gave an extra prescription which gets rid of Lorentz violations, fine, but it could not be done in non-ambiguous ways. So their prescription doesn't get what is happening, and ambiguities remain. And that was the situation of the Lee-Wick models. So to see what happens, let's go back to the bubble now, and we compare in this transparency what happens in the usual case, non-higher derivative, normal propagator. We will review it again, and then we will see in the next case, the higher derivative case. Okay? Usual case. Propagator, no prescription, bubble. The location of the singularities of the propagators is they are on the real axis, and you calculate your bubble. You take the product of two propagators and integrate the loop space momentum on R3 and the loop energy on Minkowski or Euclidean. They are equivalent in this case because there is no obstruction in the first or third quadrant. When you integrate on the energy, you will use the residue theorem and you will get some integral on the loop space momentum of some integrand. Fine. The resulting function is analytic anywhere the integrand is regular. So you concentrate on the singularity of the integrand and you will see where they are. The singularities of the integrand are where the second propagator, for example this one, is on shell with the residue of the first propagator. So it's the same thing. And that gives an equation which is the external energy is equal to the sum of two frequencies, which is related to the physical process we will see in a moment. So if you want to see where this is singular, you have to check, to draw this geometric locus in the P0 plane. Space P could be fixed, for example, while the loop space momentum K varies on the entire domain R3, and what you get is two branch cuts. That's all. That's what we expect. You just get those two branch cuts. Not only the singularity of FKP, which is the non-analyticity of the diagram, is the one that is predicted by the optical theorem. Basically, you take the bubble diagram, you divide it into two, and so you will see that the imaginary part, which is the discontinuity, which you get circumventing the branch point from above or below, is equal to the cross-section, the total cross-section of a process in which the external particle decays into the two particles in the loop, which were virtual, but in this branch cut they become real. And so you can check that this is an identity that is satisfied, as the general theory tells you. Now in our case, something changes. This is the bubble. Now this is the propagator with four poles. This is the Lee-Wick integration path for the loop energy. And so you integrate the product of the two propagators on the loop space momentum on R3 and on the energy, but the energy you integrate on the Lee-Wick path or the Euclidean, which is the same. You will get a certain sum of residues. Again, you will have a certain integral or a certain function on D3K space. And the function will again be singular when the external energy is the sum of two frequencies. But now the frequencies have complex masses because the poles are k squared equal to plus or minus im squared. And so you will have an imaginary part, but that will be associated with an unphysical process, a non-acceptable decay of your particle into two particles which have complex masses. So unless you do something better, your theory predicts something unphysical. Or you violate unitarity, you say, okay, the optical theorem doesn't hold, and then I forget about it. But if the optical theorem holds, then what you get here should be some physical process. Okay, so this is the situation. The situation is a little bit more complex than that, because now let's plot the location of those singularities when the loop space momentum spans its domain, and you will see that they cover extended regions. There are many regions because there are many signs here, plus, minus, there are 4 combinations, and the regions are 3 just because 2 of them give the same region in the middle. Let's focus only on this region, which is the only one that contains the real axis which we are interested in physically, so those are not important. So basically, when your external momentum happens to be inside, the result of your diagram, you can verify, is not analytic and not Lorentz invariant. It's what Nakanishi predicted and had noticed soon after the Lee-Wick paper. But you can expect that, because you see, Lee and Wick give you this funny integration path for the loop energy, which somewhat covers also complex energies. And if you insist to integrate the loop space momentum on real values, necessarily you can clash on with Lorentz invariance. So you must deform the integration domain on the loop space momenta as well, complexify them, and do all this work and check if there is a deformation that leads to the right result. So the prescription needed to be completed, and there was a lot to do. So first time I found this, okay, I thought, okay, now I found why they have to be dismissed. But then this problem could be solved, and so I could not dismiss them, the Lee-Wick model, so quickly. So basically, you have now to go on and say, okay, you integrate on the Lee-Wick path, but then you integrate this on some domain. What happens? It's very nice to see it in 2 dimensions, where you have only one complex, one space momentum, and you complexify it. So you study now the complex plane of complexified kx. The integral, according to Lee and Wick, should be on its original domain, real values. Well, you find that if you deform it like this, the final domain will be just like that. It's very, very simple and natural. Though that region shrinks into a branch cut, precisely what you would want. And you can do everything like this in all dimensions and for all diagrams and to all orders. In this paper you can find the proofs to all orders. So you can say, fine, we get rid of the Lorentz violation and the non-analyticity of the amplitude, just because you have a branch cut, and you can treat it as Feynman told you. You can go from above or from below. Again, that's not going to lead you anywhere, because the crucial thing is that if you do what Feynman told you, namely you go from above or from below, you have a discontinuity. And that is associated here with an unphysical process, which you cannot accept. So this is just the first thing you have to do, this deformation, to remove, not to solve the problem, but to remove a nuisance that the problem carries with itself, which was this extended region, instead of having a nice cut. But the point is that when you do that, you get immediately the idea of what is the right thing to do. Because since you start from an extended region, you can say, okay, let's start from the extended region, which is the wrong one, with the wrong integration domain. Let me go inside that region. Let me compute the diagram there. The result is wrong, finally. I don't worry. The result will be non-analytic and Lorentz invariance, and not Lorentz invariant. And then I do the deformation while I am inside. So instead of circumventing from above or from below, I go inside, I view the result of the integral as a function of its domain. I deform the domain so as to shrink this, and the result, miraculously, will be analytic and Lorentz invariant. Well, it's also a very simple result. You can prove it with a general mathematical theorem. The result will be just the average of the 2 analytic continuations, which is why it is analytic and Lorentz invariant. So the result is the arithmetic average of the 2 analytic continuations, which is a non-analytic operation, which is why in the end we won't have analyticity, but only, we'll see in a moment, region-wise analyticity, which is why the Wick rotation is not analytic, and so on and so forth. But analyticity is recovered in every region, and the Lorentz invariant is recovered. Let me go make a comment on to describe to you what this average continuation is in a simple example, how it works. Consider the logarithm. A typical bubble diagram in 4 dimensions gives a logarithm. So this is an example that is physically important. It has a branch cut from 0. Let's take the negative real axis. Now, if you want to go to the negative real axis by analytic continuation from above, you should deform your cut, for example, here, which is like writing this. If you want to go from below, you should deform the cut like that. Now, take the average, the sum divided by 2 of these two things. You will get a certain function, but you will have 2 cuts now. And you will have divided the complex plane into 2 disjoint regions, in one of which you have the logarithm, and in the other one you have the logarithm with a minus sign. On the real axis you can write this: 1/2 the logarithm of z squared. That's why you have 2 regions. So basically what happens is that the complex plane of energies, the external energy, is divided into disjoint regions. But the point is that now there is no imaginary part inside or outside. Here there was no imaginary part because we are below the threshold. Here there is no imaginary part because everything in the construction is real. The prescription was real, and this result is real. And this is how you can make analyticity, the optical theorem, work. Let's see it. Yes.
What happens when you try to cross between the disjoint regions? You get is the functions continuous and differentiable? But
no, the function is continuous. Yes, it happens to be continuous, but
not differentiable at some point. Or I mean,
no, it's not analytic. It's like going. It's like a branch cut. It's only that I have 2 branches. So what happens is the following. This is the generalization of analyticity. Normally, you can say the following thing. Normally, you have an analytic structure like this with just 2 branch cuts. So if you can say, if I compute my amplitude in an open set anywhere, I know the amplitude everywhere by analytic continuation. I will discover that there are some cuts somewhere. Fine. Here you have to change it like this. You can say that if you know your amplitude in an open set of the Euclidean region, then you can know it everywhere, unambiguously, everywhere, but not by analytic continuation. So you go by analytic continuation everywhere you want in the so-called Euclidean region. At some point you will find a branch point, and if that branch point is associated with a Fakeon, which means associated with an internal particle that you want to quantize in this new way, associated with that, because every branch point is associated with a cut. So if that cut crosses a fake line, fake particle, then you cross from the Euclidean region to the other one by means of the average of the 2 analytic continuations. That creates the new region. Here, what happens here and there, that's like a cut, so nothing mathematically interesting, but here we are not in a physical region because we are in, we have real complex energies, external energy. So now the optical theorem works as follows. you have that if your external leg is physical and your internal leg, one of them or two, are fake, then there is no imaginary part by construction. So this is zero, no discontinuity. The optical theorem then tells you that this should be equal to the cross-section for the production of the fake particles out of the physical one, which is zero as long as you project those physical particles away from the physical spectrum. Yes. So that's what you have to do to close the circle. And actually, that's what you can do, but you can also see that's what you have to do. You have to project the Fock space onto a subspace that does not contain these the degrees of freedom quantized this way. And that is why they are called fake degrees of freedom, because there is no way to produce them and no way to create them. Normally, you look the matter the other way around. Normally, when you have something you want to throw away, let's call it ghost. What we had at the beginning, what was a ghost. You can say, okay, let me throw it away. I just do it. I throw it away. I don't want to consider it in the physical spectrum. I assume that the physical spectrum is just a subspace. You can do that. That's your choice. But the point is that the unitarity equation is quadratic, which means that yes, you can project the range of the indices I and j, the initial and final state, wherever you want, but you cannot choose the range of the sum in between. It's quadratic, so there is a contracted index. You have to show that if you project something away, it is not generated back by this equation, which means by an imaginary part. So that's why normally you cannot project anything away unless you destroy unitarity. And this here is a case in which you can, and actually you have to, because the fake particle does not generate discontinuities or imaginary parts. And so the optical theorem works fine. In general, when you have the standard model, for example, with many bubbles where many particles circulate in between, only the real particles will contribute to the imaginary part and the cross-section, and the fake ones will be invisible to the optical theorem. And that's how you get rid of those unphysical poles. When you quantize as usual with the creation and annihilation operators, you just project your Fock space by declaring that your subspace, the physical one, is obtained by acting on the vacuum only with the creation operators of the particles that you call physical, that you have quantized with a plus I epsilon prescription. Those that you have quantized with the other are to be not used. And the free Hamiltonian, even of a higher derivative theory, that normally is not well defined, it's well defined, but normally it is not positive or bounded from below in the total Fock space. It is bounded from below in the projected Fock space. The average continuation we have seen. So now let's come to gravity. So we have seen that a logarithm in the physical quantization prescription goes into this function, which has a discontinuity. It goes into this other function, which breaks the plane into different regions, but has no discontinuity. And so the natural thing is to say, what about taking this higher derivative action of quantum gravity, which is renormalizable but not unitary, when you quantize all the poles a la Feynman, and we take the poles of the propagator, the free propagator, expanding around flat space, and you quantize a la Feynman the graviton. But you quantize as a fake particle everything else, or at least you need only one degree of freedom to quantize this one. Let's see in more detail what happens. So this is a higher derivative theory, but you can, by means of auxiliary fields and some simple field redefinitions, translations, and dilatations, you can rewrite it as a theory with no higher derivatives. Then its action is like this. You have the Hilbert term, then you have a scalar field phi with this action here, complicated, but then you have a spin 2 field chi with another action that is a little bit long to write. It's a bit implicit here. And then if you want, you can add the covariantized standard model, which is the meta sector, and when you do the same operations, it depends on the metric in this way. So basically, you have a graviton multiplet now. The higher derivative theories can be decomposed into three fields: the fluctuation of the metric around flat space, a scalar field, and a spin 2 field. Now, the action of the graviton is the usual one, of course, no problem. The action of the scalar field is a bit unusual, but no problem. The coefficient in front of the kinetic term is positive. The point is this parameter zeta is positive, by the way. You have to choose the signs of these parameters to be positive. Positive, positive, positive. That's compulsory to have real squared masses. And once you have chosen those signs, there is nothing else you can do, and you will see that the quadratic part of the chi action has the wrong sign. This is the meta part. This has the wrong sign. And the derivative, the two derivative kinetic part, which is implicit here, also has the wrong sign. It's a Pauli field action covariantized with the wrong sign. Necessarily so, this chi mu, which was the problem, must be quantized as a Fakon. But when it is quantized as a Fakon, the problem disappears. There are some new things, however, some remnants of this thing, the Fakon. And now I describe the physical predictions of this theory. One is the violation of microcausality, which happens, for example, one thing that you can do when you have a muon, a particle that can decay, is to compute the width of the muon, its lifetime. If you compute the width of the Fakon, chi mu, which comes from the absorptive part, the imaginary part of the graviton multiplet one loop self-energy, you will see that it is negative. You can find these calculations in two recent papers by myself and Marco Piva. By the way, the coefficient is also known in conformal field theory as central charge. It's something that receives contributions only from the matter fields, not from the graviton and not from the Fakon itself. Maybe from phi if phi is quantized as a physical scalar. It is quantized as a Fakon as well, then C does not receive contributions from phi. So this is a scalar. It could go inside here the number of scalars, number of fermions, number of vectors. Now, what is a negative width? Is it so troubling? Is it so worrying? No, it's not so worrying. Let's see what happens. So basically you have a propagator, and when you resum the bubble diagrams, all the whole geometric series, you end up with this correction. And if you check the imaginary part of this, so remember we have the wrong sign in front. The imaginary part is this. But since our theory now satisfies the optical theorem, this must be positive. And so, since you have changed the sign in front of the residue, of the sign of the residue, you have consistently, you will find that your gamma is negative to have the product positive. So consistently, this gamma is indeed negative. Fine. Now, what does it mean? take a Breitwig formula, particle at rest, just to be simple, and study the, the Fourier transform. The Fourier transform has a damping factor e to the minus gamma t over 2. Well, that remains a damping factor because that's the Fourier transform of an L2 function. No matter what the sign of gamma is, it cannot blow up. So normally one thinks, oh, but then if I change the sign to the lifetime, the exponential blows up. That's impossible. You cannot generate something blowing up as Fourier transform of an L2 function. The point is that in front you have a theta function. And you can check that the theta function is the theta of gamma t. So if gamma is negative, that theta picks the future instead of the past. And that's how a negative gamma simply reverses the sign of that normally would determine if your theory is causal or not. Moreover, there is this oscillating factor here, which is the mass of the Fakon, and that means that all violations of microcausality will be suppressed for energies larger than the mass of the Fakon, when the oscillating factor will average all of them to 0. Okay, that's nice, that's a prediction, but you can say we will never be able to test it in high energy physics, because even if the mass of this Fakon is unknown, and it could be, as I hope, much smaller than the Planck mass, still it's expected to be large. It could be 10 to the 12, 10 to the 10 GeV, whatever. So another interesting thing is to study the classical limit of this theory, because you will check that there are corrections to the equations of general relativity, and in those corrections, the violations of microcausality survive. And it might be possible to study them non-perturbatively, just looking for exact solutions or how the exact solutions of general relativity are affected. And you can find that the general final equations have this form. G mu nu, the Einstein tensor, is not equal to the stress tensor of the matter part, but some average, which is an average that is sensitive to the future and to the space-like separated parts. Okay, so let's see this now to conclude. This will be the final remark. So, just conceptually to tell you what happens, morally speaking, is that now let's use this action with 3 fields, non-higher derivative. If you derive the field equations, you will have 3 field equations. Okay, fine. These are the field equations. They look complicated, but they are complicated. The equation for the metric, the equation for the scalar, and the equation for chi. How do you project away the fake particle in the classical limit? You should solve the equation of your fake particle with the prescription of taking half the sum of the retarded and advanced potentials, because the classical limit of that propagator now is exactly the principal value. Although the principal value cannot be used inside Feynman diagrams, in 3 diagrams it can. And so now it's safe to do that. And the solution you insert into the other equations, and that gives you the projected equations, or if you want, you can insert it into the action, and that gives you the projected action. So basically, you have a new step to make in your quantization process. You start from a local action, which was the higher derivative one, for example. And that is not the classical action, because that has 4 derivatives, and it is unprojected. It has some fake particles going around. So at the level of quantum field theory, you have to project a Fock space. At the level of a classical theory, you have to project the configuration space. Otherwise, it's too large. So I call it interim classical action. You can think of a gauge fixed action. When you have an action with a gauge fixing and the Faddeev-Popov ghosts, that's local, that's fine to work with, but unprojected. So you do not take it seriously to check positivity in the Euclidean, to check what happens as far as the field equations of the gauge fixed action are concerned. But it is very convenient because the projection, solving the gauge condition, would make it non-local. So it's very convenient to use a gauge-fixed local action. So you have an interclassical action. So the correspondence principle will work in a funny way because you start from a classical action that is absolutely not even classical. You quantize it, and then you classicize the quantum theory, and you go back to the projected action, which is non-local. And those non-localities are the signs of the violation of microcausality. In a simple toy model, I can show you with some concrete example that we can see. So let me take a non-relativistic system, mv squared divided by 2 minus a potential, and add higher derivative terms, the square of the acceleration with a constant tau. The field equation, this is unprojected. The field equations are like this, and these have higher derivatives, so in principle, to solve this equation, you would have to fix position, velocity, acceleration, and derivative of the acceleration at time 0. What you do is to project something I forgot to write here. You write this like this. And then you move the parentheses here on the other side. The point is that the Fakeons prescription gives you a unique prescription for that green function. That part of the green function has no degree of freedom because it is uniquely prescribed. It is the principal value, and it gives this kind of average oscillating function. You can check that it is a well-defined distribution, and it tends to 0 when you suppress the higher derivative term that you have introduced. But you see that it is not causal, in the sense that to predict the present, to solve this equation, you need to know the external force in the future, just to write the equation. So that's how physics would look like in this kind of theory. When you go to very, very small distances, how small we don't know because it depends on the mass of the Fakon, you will see that present, past, and future don't make any sense anymore. Cause and effect do not make any sense. And to summarize, the principles that are satisfied by this theory are unitarity, locality, a form of renormalizability that now I need to make more precise than strict, super, which I call proper renormalizability. Namely, I require that the gauge couplings be dimensionless. So the Newton constant should be dimensionless. Otherwise, I can construct infinitely many theories that are of quantum gravity that are super renormalizable, precisely in the same way as I have Yang-Mills theories that are super renormalizable in 2 dimensions or 3 dimensions, even without fake particles. So you need, it seems to be true that from the standard model that the gauge coupling have this interesting particular status. They have 0 dimensions, not non-negative, 0 dimension. And then the model is unique. These are the symmetries. Again, you don't have analyticity, but region-wise analyticity. And instead of causality, you have just causality at large distances. Otherwise, you have violations that maybe could be detectable. To conclude, quantum gravity is identified in an essentially unique way. The gauge interactions are identified uniquely, but only in form. You cannot predict the gauge group. The matter sector is basically unrestricted, which again is a sign of us becoming powerless. All attempts like unification, grand unification, all attempts to answer this question, to fill this gap, have failed. That's something that you should consider. The major prediction is the violation of causality at small distances. That's the only, in the end, this correspondence principle is very conservative, you see, because we didn't give up anything, basically, just microcausality. The classical limit is not described as starting classical action, so okay, it isn't. The mass of a Facon could be much smaller than the Planck mass in nature. I hope so, because that would mean that we have hope to detect signs of departure between general relativity and this theory. And then one can say, before I ask the following question, since gravity works because there is this fake particle, so gravity predicts the existence of at least one Facon, which has spin 2. Instead, phi could be a Facon or not. It's not really necessary. Basically, at very large distances, the mass of this Facon becomes negligible, and it makes the whole triplet, graviton, Facon, chi nu, and phi, stick together, and that's why they cancel each other non-renormalizable divergences. That's necessary to make everything work. The question is, however, are there any other Facons in nature? Because once you have one, there might be others. And actually, since this is a prescription, it's not Lee-Wick models. It's, you know, the theory in the end that I consider is not of the Lee-Wick type, because in gravity, a Lee-Wick model would need more higher derivatives than these. And these are just poles on the real axis that are split and then go back. The question is that you can turn everything into a Facon now. And so you can build a standard model with Facons by adding, as long as they are massive, otherwise you violate causality at all distances. And so among the other particles, the particles we already know of, can we exclude that there are Facons? What about the intermediate bosons Z, W? What about the Higgs? These are particles that we do not see directly. We just see the decay products of those particles. Well, from the decay product of a fake particle, you cannot distinguish it from a physical particle. That's why it is a fake particle. It simulates a fake particle. You cannot throw away from the spectrum something that is inside the diagram. So if the fake particle is inside the diagram, it's there. The point is, however, that we have seen that the imaginary parts of diagrams are affected by being a Facon or not, being the virtual particles a Facon or not. So you have to check if in the data the imaginary parts of the loop corrections containing Z, W bosons, Higgs fields have been tested already or not. And it happens that every imaginary path has a threshold, as we have seen, this branch cut. So if the energy is small enough, you do not even test it. And in this famous peak, for example, all the imaginary parts of the intermediate bosons contribute. So they cannot be fake, otherwise you would have already noticed a discrepancy. But the Higgs boson has not been reached in Lab 2 because they stopped at 2. Lab 2 stopped at 210 GeV or something like that. But you would have this Z giving a Higgs Z, this kind of bubble. But the threshold is the sum of the masses of H and Z, which is 125 plus 91. 216. So this has been missed. And it would require some precision measurements because it's a one-loop correction. I'm not sure it can be done at LHC. In a linear collider, however, it could be done. Thank you very much.
So, let me just understand this, some basic questions. So, if I do graviton scattering, when I get the energy of the scattering above these Fakeon masses, it just switches off, right? Is that right that the interaction just vanishes because there's a cancellation?
So if you have graviton or anything here, that produces a fake particle. So anything, it could be E plus, E minus, because they couple to the matter sector as well. So that produces chi mu nu. Then the point is, are you going to see that chi mu nu or not? Because if you let it decay, you will never see any difference between a fake particle and a non-fake one, unless you go to precision measurements and check the loop corrections. If you instead want to see a muon, like say a mu, you want to see it instead of letting it decay, that you will not see. You just don't see it, because it's not there. There is no E plus, E minus, chi mu nu. This cross-section is zero. It's not in the final states, but it is in the intermediate state. So it's something that mediates an interaction without becoming real in the end. And funny enough, it can decay. So basically, you can just view this as a 4 vertex. I have just renormalized the theory by, as in the Fermi model, right? You introduce intermediate bosons to make the theory renormalizable. Here you introduce Fakeons, because if I treat it like that, it's not only non-renormalizable, it's non-local now. It's like integrating out the fake particle. So the fake particle, you can imagine chi mu nu as a sort of auxiliary field with a kinetic term. Integrate it out, and it will bring those averages around your theory, non-localities and violations of microcausality. Instead, if you integrate a normal auxiliary field out, that's algebraic, and you don't care. So this is the only thing that you cannot see. And it's hard to, for example, the Higgs. There is no hope to see the Higgs. There is no hope to see the Z0 alive. And so we have to answer these questions indirectly.
Do we have further questions?
So my second one is, well, and what happens to Schwarzschild solutions? As I make my planet smaller and smaller, presumably at some point I go through this guy's mass at the distance scale of the black hole-like thing, and what happens then?
Yeah, this is something that we are considering right now, and actually I find that there are a lot of questions, even in general relativity, about black holes, how to describe the singularity, for example. And so the question I have is how to describe the source of the Schwarzschild black hole. How to describe the source. Normally, if you have the Coulomb force of a point-like charge particle, that you know that the source is a delta 3 statistic. What coordinates do you use? Well, that's very difficult to say. That's a well-known problem, but it would help me, because I think that here in this theory the description would change, the description of the source. Formally speaking, if you put the equations in vacuum, G mu nu equals 0 is still a solution, because these higher derivative terms are all proportional to the Einstein tensor G, big G mu nu. So you would say Schwarzschild is still there. The solution is still there. That's in vacuum. So the only thing that I can consider is how to describe the black hole while it forms, or to describe in the sense of distributions the source. But this is a well-known problem, and people have tried, but still there is no. I have not much more to say about that right now, other than saying that it is very, very interesting to explore this and the cosmology, the effects on cosmology.
Which kind of effects?
For example, what happens of the Friedman-Robinson-Walker solutions, what happens during the Big Bang, right after the Big Bang, how these, because you know, the hope is that since you have some equations that might be complicated, but you have them. I can put them in a computer in the case of a metric that depends only on time. That can be done. They are still complicated even for the computer, but if we find some exact solutions, or how the known exact solutions are modified, maybe we can search for effects, or even just interpreting the data, put bounds, because there are the bounds on these masses, m chi and m phi, are very weak. I didn't even discuss them, but I think that if you put bounds from black holes and from the law of Newton, those masses can be unbelievably small, of the range of MeVs, without affecting anything we have seen so far. So certainly going to that direction would would allow us to say, okay, these masses are bigger, than improve some knowledge there about. And the effects they might have on cosmology, because in cosmology you also discuss about violations of causality, or causally disconnected regions. That's not my domain of expertise, for that has not been so far, so I have to learn a little bit of new things, but I find it fascinating. So.
But usually it's solved with inflation.
Yeah?
So usually it is solved with inflation.
But
so this will provide a new solution.
Presumably there will be because inflation, for example, is a framework that you can describe with r plus r squared, which means a scalar, which might not have this potential, another potential. Now there is this extra thing that must be there because the theory predicts that it has to be there, otherwise will that change something of the CMB spectrum? I don't know, maybe it is a meaningless question and somebody can tell me, no, that you're wasting your time, and it doesn't. But since I'm not an expert in cosmology, I can presume that maybe something to look into and see if there are effects there.
Okay, thank you again for your talk.